We looked at the exponential function. Let's now look at its inverse, the logarithmic function, see how we handle that one. So if we have y equals, I'm talking about natural log here, natural log of some function, it ends up being the derivative over the function. So the derivative over that function. If it's some other base, similar to what we saw with exponentials, but because they are inverses, now we divide by the natural log. And this is where we've got to be careful. So exponentials, when we differentiate, you multiply by the log of the base. And when you integrate the exponential, you divide by the log of the base. Logarithms are the inverse, so it's the other way around. Differentiate the log function, you divide by the log of the base. I won't talk about integrating logs right now because that's a totally different thing, which we'll see later. So you get the log of 3x plus 5, it's simply derivative over function. So 3 over 3x plus 5. Log of x cubed. Well, you've got a couple of ways you could do this. I could say, well, log of x cubed, derivative over function. Got some cancelling that'll happen. I get 3 over x. Of course, I could make use of log laws and say log of x cubed is 3 lots of log x. Differentiate log x, I get 1 over x. So I've got 3 times that, 3 over x. I guess it's just however you're thinking at the time when you do the problem. The log of log x. So I am differentiating a log function. Derivative over the function. Now the function is log x. Its derivative, oh, it's a log function. So its derivative over function. We end up with 1 over x over log x. That's messy. Tidying up. That x comes to the bottom. We get 1 on x log x. Again, a couple of ways of approaching something like this. Log of x plus 3, x plus 2. Derivative over the function. Well, I got to use a product rule to differentiate it. Write down the first, diff the second, plus write down the second, diff the first. Tidy up the top, we get 2x plus 5. Now, that was okay because we had a fairly simple product there. Could have expanded out, I suppose, and did it that way too. But another way we could have done it, use the log laws. Split it up into 2 log functions. And both of those log functions very easy to differentiate. Now it depends what I want to do with the derivative. I mean, that's an answer for the derivative. Now if I wanted to find stationary points or something like that, okay, I need to combine it into one fraction. So I can say, well, that'll equal 0 and so on. So a bit of algebraic fraction work and you'll see we end up with the exact same algebraic fraction as we got on the left hand side. Similar idea here. This one here, derivative on function. When I differentiate this, I've got to use a quotient rule. So on the top of the fraction, square the bottom, write down the bottom, diff the top, minus write down the top, diff the bottom, fraction on fraction. Alright, still got some cancelling there. The x plus 2 will cancel with the x plus 2 squared. I end up with that. If I use my log laws, this time it becomes more efficient because 2 simple ones to do. Playing with that, I just got to get a common denominator. Bingo. Personally, I think in this case the splitting into the 2 created an easier question for myself than the left hand side. Not that much more, but you know, again, personal preference, however you want to deal with the situation. Base is not natural, it's not E. It's okay, I will do it like normal, but also divide by the log of the base. So differentiate the log of 6x. Derivative over function, but I've also got log of 10 on the bottom. 6's will cancel. 1 on x log 10. Okay, now we can really have some fun. Our first triple.